এমনি হাঁটু তো ক্ষয়ে যাওয়া আর্থারাইটিসের প্রবলেম, আর তার জন্য ডাক্তার বলছে যে এই অবস্থায় যদি মানে হাড়ের কোনোভাবে ভেঙে যায়
আমার পায়ের কি অবস্থা বাপরে বাপ, কষ্ট করলাম বলতে ঘরে তো কাজ বাচ্চা থাকলে তো কাজ করতেই হয়, তাই কতক্ষণ বসে থাকা যায় আর ওদিকে একটু পর খাওয়া যায় গিয়ে থাকলে কি করে দিই, তেমন কি খাওয়ার কোনো হবে না, চাউমিন করে দিতে হবে, করে দিতে হবে।
Welcome, Professor Rahman. I am really thankful to you and I welcome you on behalf of the Alipurduar University. And now I'm going to introduce you in front of our students and our esteemed resource persons, our research scholars. Professor Shoidur Rahman is currently working as a distinguished research professor and head of the Research Center for Nanomaterials and Energy Technology at Sunway University. He is also working with Lancaster University as a full professor. Previously, he worked as a chair professor at the Center of Research Excellence in Renewable Energy at King Fahd University of Petroleum and Minerals, Saudi Arabia. Prior to joining that institute, Professor Shoidur worked 18 years in University of Milan. Clarivate Analytics, Thomson Reuters awarded him highly cited researcher for being among the top 1% researchers for most cited documents in his research field for the 8 consecutive years. Sorry for the inconvenience. In 2019, Professor Shoidur won Vice Chancellor's Award for Achievement in Research, Sunway University. Professor Shoidur published almost 550 journal papers, mostly in top-ranking high-impact journals. He is ranked number 1 by Web of Sciences on nanofluid research-related topic. He has more than 70,000 citations with an each index of 134 according to Google Scholar citation. He has supervised more than 80 postgraduate students so far and has secured and managed more than 25 million ringgit research grants as a PI and member. Professor Soidun is working in the area of emerging nanomaterials, MXNs, and their applications in energy storage, heat transfer, solar energy harvesting, and environmental remediation. We welcome you and thank you, sir, for your cooperation and giving us your valuable time. Thank you, sir. Now, may I request you for your presentation, sir?
Thank you, Dr. Rinku, for the introduction and also for inviting me to share my experience. Is it clear? Can you hear me properly?
Yes, sir. Yes, sir. You are completely audible, sir. Please carry on.
Okay, let me share. Yeah, I normally don't use much this platform, Google Meet. So my sharing button just not showing. Can you see the screen?
Yes, sir. But yeah, it's perfectly.
Yeah, just 1 minute. Can you see in the presentation mode?
Yes, sir. You can continue. Then only we can see that the slides are moving or not.
Yeah, it's not moving. You
So
can
maybe
see
you can. Yes, sir. I can see, but you should go for the presentation. Sir, cup kind of sign is there. Umbrella kind of sign is there. So.
Yeah, but it's not. Yeah, it's not working. Yeah, sometimes this platform actually does not work for this presentation mode. Yeah, let me stop sharing and try again. Because it's not moving. Yeah, just wait for a while. System does not work sometimes. I'm trying to convert it into PDF. Yeah, please bear with me. So I'm trying. Hmm. Yeah, I made PDF, but files are not moving. I don't know.
Sorry to interrupt you, sir.
Yeah.
Actually, in PDF, you need to change manually. So try that one, please.
Yeah, slides are not moving either PDF or also PPT.
In PDF also, sir, try to just scroll down.
No, it's not moving. The scroll down, yes, I know the scroll down, the arrow button, nothing is working. Normally, this. Yeah, cannot move, sorry.
So please, sir, try with the PPT again.
Okay, let me log out and try again, okay?
Okay, sir, yeah.
Sorry, it's not moving.
Sir, if possible, can you go to the presentation mode
Click on the slideshow.
or click on the slideshow?
Yeah, I am aware. Maybe I send a slide and one maybe can control from your side. That's only the possible option I can see. Let me send the file to Dr. Rinku.
Okay. So you can send the file also. Yes. Okay.
I have sent a file, both PDF and PPT. Can you check, Dr. Rinku?
Yes, sir. We are downloading and sharing the screen.
Yeah, okay.
তাহলে পরে করে নেন
এটা কাজ আছে, এটা কাজ আছে তো ল্যাপটপ না
ওই যে সেমিনারটা হচ্ছে না
বুঝছি অনলাইনে দেখা লাগে
হ্যাঁ
থাকতে লাগে
হ্যাঁ ওখানে চেক করতে হচ্ছে কেটে গেছে কিনা পুরো লাইভ হচ্ছে তো
Is it ready?
Just a minute, sir. Yes, sir. Sir, kindly proceed, sir.
Okay, thank you very much. Hello everyone, Assalamu alaikum. Thank you for inviting me to share my experience. Sorry for technical problem. Can you unmute Arif Islam? Otherwise there are little bit noise. Okay, so I will be talking on this advanced material. After graphene, this advanced material magazine is invented in 2011. So we are in Malaysia, pioneer in magazine synthesizing. We have some expertise and where these materials can be applied, particularly in energy storage and thermal performance, which is aligned with the focus of the seminar. Okay, so I'm also working with Lancaster University. So basically I'll be sharing these advanced materials in energy storage and thermal performance area. Also, can you make the screen full? I cannot see much, very small. Okay, and then proceed to the next slide. Next slide, please. Can you hear me?
Yes, sir.
Next
You are
slide.
audible.
Next slide, please. It's not moving.
So actually, I'm moving the slide here, but actually it's not showing in the screen that is moving. So just I'm fixing it. Bear with me for 1 minute. I'm just making sure. Okay, please.
Yeah. You can try the PDF also.
No, sir. I'm trying.
Yeah, okay. Keep on trying. Yeah. Okay, I can see the second. I can see the third slide. I don't see the second slide. Okay, now you can move to the second slide.
Yes, sir. Please carry on.
Yeah, second slide. I don't see the second slide. Yeah, okay, I can see the second slide. So this slide, as you can see, the top priority, top 10 problems for next 50 years. When we want to conduct our research, when we want to carry out our research, so we need to be very strategic where we want to work. So for example, global grand challenge areas, niche areas, top 10 problems for the humanity. So as you can see, the energy, water, environment, which will be my focus, is actually according to one of the Nobel laureate from Rice University. He identified these top 10 problems. So energy, water, environment, which is the focus of my presentation, will be discussed. So this is basically strategic way of identifying our research area, focus area, so that our research topics are impactful, aligned with the global grand challenge research area. Because simply if we do research without doing our homework, without strategic areas, niche areas, it will not give us impact. So that's actually some of my work. We are working in the area of magazine, advanced materials, aligned with these global grand challenge areas. Next slide, please. So these are basically the major problems in energy thermal areas. So as you know, when we use our solar energy, in the solar panel, it is overheated due to solar radiation. So this is one of the problem. Overheating is one of the problem. That is also called thermal problem. In electrochemical energy, low energy density, power density, these are also challenges. And when we use materials in chemical reactions, so reactions are also, for example, in fuel cell, very slow, sluggish. When we use advanced materials, for example, nanomaterials, magazine, graphene, CNTs, these are also very expensive. Charging duration of charging, for example, electric vehicle, it cannot go more than 500 kilometers or miles. So this is also another problem. So nanomaterials, when used in certain application, also fire hazardousness and availability of materials. Some materials are available only certain locations, and energy storage also in low scale, for example, in portable devices. So utility scale energy storage is also another challenge. Materials are also not stable. For example, when we use them as a fluid, large scale production of nanomaterials. So there are many challenges basically in the area of heating, energy storage, material, cost, stability. So many problems basically. So my talk actually will address some of them: overheating, low energy density, the cost. We also develop this material using recycled materials to reduce the cost. Okay, next slide, please. So this is how we develop our materials. So this materials is called the precursor materials, max space. That was invented in 1960, but one of the layer, its middle layer, how to eliminate, was not invented until 2011 by chemical reaction, that is called chemical etching process. That chemical etching process actually was invented by Yuri Gogursi from Drexel University, and we learned from his publication and some of his team members, and we successfully synthesized in our lab in Malaysia at our RCNMet lab as well. As you can see, the chemical reaction is taking place. That is called etching process. By the etching process, one of the layer, aluminum layer, let's say the Ti3Al(C2). So middle layer, aluminum layer, by chemical reaction, etching process is removed, and then subsequent processes are done to purify it, to make it pure magazine. And then we apply thermal performance application, energy storage application, and there are many applications I will highlight in one of the slides. Next slide, please. So these are the history of emerging materials. So CNTs were invented in 1991, and then graphene, and then 2011 this magazine. So why new materials? So as you know, no materials are perfect. So in terms of graphene, so it has some of the challenges like rigidity, its band gap. So it has some low band gap, and its rigidity is also not that strong compared to magazine. So basically no material is perfect. So to overcome some of the challenges of the existing materials, new materials are invented. That is basically the some of the reason. And also it has layer, it has different structure. So I will share all those in subsequent slides. Next slide, please. So this is a magazine, how it looks like. So if you want to know or ask that what is this material, this is the answer. As you can see, it is a two-dimensional layered materials. So in between there are layer. It is also two-dimensional. So it has length and width, but its thickness is nano size. That's why it is called nanomaterials. So in between layer there are layer. So in that layer actually some other materials can be embedded, can be inserted. So this is, as you can see, the accordion-like clay materials. So this is how it looks like. You can see the SEM image, you can see the TM image. Okay. So next slide, please. So this is actually the origin of this material. So if you want to know more, so I'm discussing only one types of magazine, Ti3C2. But there are varieties of magazine can be derived from max phases. So there are M elements, there are A elements, there are X elements. By combining these, actually, you see under M there are number of elements, under A there are number of elements, and under X there are number of elements. So by combining these, actually we can get a number of max phase, and from there actually we can get diverse types of magazine. But so far Ti3C2 is the most versatile, most extensively studied materials. However, there are other types of magazine and max phase can be developed. Next slide, please. So these are history of invention. So it was invented in 2011, and then subsequently there are other types of magazine materials are invented, developed. There are also different etching processes, top down, bottom up. So different types of etching process also invented. Initially it was etched by hydrofluoric acid. As you know, hydrofluoric acid is very detrimental, dangerous acid. So later on, subsequently, some other mild etching process, for example, hydrofluoric acid with lithium fluoride in situ reactions are developed to avoid this hydrofluoric acid. There are molten salt and many other synthesis processes are developed over the years. Okay, next slide. Next slide, please. So this is the layer structure. As you can see, the max phase Ti3AlC2. So it has Ti elements, titanium elements, it has aluminum elements, it has carbide elements. So main purpose of this one of the layer, aluminum layer, need to be eliminated by chemical reaction etching process. So this is showing that one of the layer, aluminum layer, is removed by that chemical reaction or etching process. And then finally you can see this is sheet. So this is magazine sheet. So it can be sheet, it can be powder, it can be slurry in different forms. It can be developed. So you can see here magazine sheet here. This is how it looks like. Okay, next slide, please. So these are some of the proofs and accessories needed to synthesize this magazine. So precursor materials and mortar and pestle. So what we do, we can get the precursor material from vendor, or we also can develop from our lab also. So all these precursor materials are with certain chemical ratios are mixed and then put into a tube furnace with 140 degrees centigrade. So with certain temperature, pressure, my team works with that tube furnace and then they develop that max phase, Ti3AlC2. So that is basically a brick shape materials at the bottom, as you can see. And then using mortar and pestle, this need to be crushed into powder. Okay. Then this powder is actually etched in chemical reaction in the fume hood in the subsequent process. Okay. Can you go to the next slide? So then that powder max phase after mortar and pestle powder form, then this is in this fume hood chemical reaction takes place. This is basically the most important part of magazine synthesis. So certain temperature, certain speed of the proof need to be there, and also the pouring. So a lot of technique needed there. Otherwise, there will be a lot of impurities will be there. So one of the challenge in magazine synthesis is oxidation and the impurity. So that's why it needs experience. So we have been working for last 6 or 7 years, and that's how we develop our experience. And as a result, we managed to get the pure magazine. So this is basically the chemical reaction takes place here to eliminate one of the layer, aluminum layer. Okay, next slide, please. So then subsequent processes need to be carried out to remove, as you can see, once chemical reaction takes place, so there will be some other impurities. So after centrifugation, after filtration, by different intermediate processes, by changing pH, actually its purity is improved. Okay, so impurities are removed by filtration, centrifugation. So there are some subsequent processes by which impurities are eliminated, and finally it is checked by SEM and XRD. This will ensure whether the magazine is pure or impure, and also we can check with the literatures, and also to see the other characterization like SPS, TM, PSM, all other characterizations also need to be checked to check completely whether this is pure magazine, what are the elements and so on. So these are basically my team will check its purity. Okay, next slide please. So no material is perfect even though pristine magazine is developed, but again it has some of the drawback challenges. So to overcome the challenges of pristine magazine, actually it can be made into compound, as you can see, by intercalation, deintercalation, delamination, hybridization, surface modification, functionalization. So its behavior, its properties, its performance can be improved by these types of processes, okay, using different types of treatment, DMF, and so on. Okay, so these are, I think, the chemical processes by which compound can be, or other materials can be inserted in between layer, and also the termination can be included. So this is one of the uniqueness of these materials. Next slide, please. So these are also some of the other ways, as you can see, hybrid engineering, other ways also, its behavior can be changed to suit specific requirement or application. Okay, this is called hybrid engineering and other ways. Next slide, please. So as you have seen, we can insert in between the layer other materials, third materials, so we can make compound. This is called intercalation. Okay. Next slide, please. So these are also called the terminals. This is another benefit. So different types of OH, oxide, chloride, fluoride. So these are the terminals also for ion attraction, ion movement. For other purposes, these terminals also has some beneficial effect. So this material has some terminals, like as you can see, OH, O and chloride and fluoride terminals also can be developed through synthesis process. Next slide, please. So these are other ways also. It can be made ribbons, flowers, other shapes also can be made to fulfill some of the specific requirement. Next slide. So this is very important slide for all of you. So you may have question, where can I apply these materials in solar energy, in battery, in crops, in desalination, in energy storage. So these are actually diverse applications of these materials. However, we are working in the area of thermal energy storage, electrochemical energy storage, battery, supercapacitor, and also in the area of fuel cell. So my suggestion is that if you are interested to work in your specific areas, I suggest to explore literature, identify few review papers that will guide you whether this is suitable in your specific areas or not. And also, we can supply these materials, magazine. We already worked with KPRIT, and we managed to publish some good quality paper in desalination. We are also working with some other Indian organizations. We supply magazine and they use in their specific applications, and we jointly publish together. So it is good news that we can supply these materials in your organization, those who are interested also. And those who are interested in specific areas, I think you can explore those areas, and later on if you are interested to work with us, we can discuss more, we can collaborate, we can meet and design a project with this magazine in your specific application. So basically, these are the diverse groups of application, as you can see, in the area of energy, thermal, solar, photocatalytic, desalination, and so on. So why? Because it has some outstanding behavior, optical behavior, catalytic behavior, thermal behavior, many outstanding behavior of these materials attracted in these diverse applications. Okay. Next slide, please. This is one of the challenges initially I showed you. So cost is one of the major challenges of different types of nanomaterials. So how this cost can be reduced, this is some of the works we have done. Okay, next slide, please. So before understanding cost, we need to understand what are the precursor materials. Okay. So carbon is one of the precursor materials, titanium is one of the precursor materials, and then aluminum also one of the precursor materials. So how to reduce the cost? We can find these carbon materials, as you know, we can get it from palm shell, coconut shell, waste tire, carbon shoot, petroleum coke. So we have collected some of this waste material, waste tire, carbon soot, petroleum coke. Okay, so we have developed some of these precursor materials rather than buying from vendor. And also you see the aluminum is also from scrap aluminum, beverage can, we also extracted. But titanium is very difficult, so we could not get the waste or recycled titanium, but we managed to get carbon and aluminum. This is how we reduce the cost up to certain extent. So cost analysis I will show you, particularly to reduce the cost. Next slide, please. Next slide, please. So as you can see here, this is how the materials are processed. So for example, waste materials, we recycle how, as you can see, palm shell, coconut shell, activated carbon. We pyrolyze through our tube furnace, and then we produce precursor materials, carbon. And then carbon is one of the precursor, as you can see, and we put into tube furnace and we make it brick shape, make space. This is how we use our waste materials to replace the carbon. Okay, next slide, please. So this is one cost analysis my team has done and also we published in journal. So as you can see, precursor materials, ball milling. So what are the costs involved? Roughly, we have estimated some of this cost based on our experience. So it cannot be stated that it is very comprehensive, but at least we try to get some rough ideas based on our experience and literature studies. So as you can see, the different types of precursor, cost of precursor materials, ball mills, tiring, so we put some cost. And also we compare with the materials we purchase from Sigma Rich, Alibaba, and also the who develop magazine, their company, Carbon Ukraine. So if we compare with their price and our price is 10 times less than their price. So this is based on some of our rough estimate, particularly to address one of the challenge of cost reduction. So we managed to reduce cost up to certain percentage, as you can see. Next slide, please. So as I mentioned, the thermal management, heat transfer is one of the challenging area where these materials, this magazine, graphene, advanced materials can be applied to remove this heat. Because why? Normally, heat transfer materials has very poor thermal conductivity. Magazine and graphene, CNTs has very high thermal conductivity. So if these highly conductive materials are used in this heat transfer application, basically this will be able to eliminate this the overheating problem in solar, car radiator, in battery thermal runaway. Okay, so these are the rules of nanomaterials, has very high thermal conductivity, heat transfer behavior, which actually will help to improve this heat transfer performance. Next slide, please. So these are heat transfer phenomena. I will not go much on this. So next slide, please. So these are basically the heat transfer fluid used in solar collector, car radiator, in different applications. For example, water, ethylene glycol, transformer oil, engine oil, distilled water. So these are the list of heat transfer fluid which has very, very poor thermal conductivity. So can you go to the next slide? So as you can see, these are the heat transfer fluid. You see that left hand side, heat transfer properties called thermal conductivities are extremely poor. For example, water 0.5. If you compare with the nanomaterials, graphene, CNT, so graphene, as you know, heat transfer or thermal conductivity behavior is 5,800. As you can see, it is extremely high. So when this highly conductive heat transfer material is suspended to low heat transfer fluid, for example, water, ethylene glycol, its heat transfer rate will be substantially improved. So I'll show you some of my slides that how much percentage improve. In certain cases, when we suspend this magazine, graphene, CNTs into this heat transfer fluid, heat transfer rate improve by 70%, 60%, 80%. So as you can see here, the heat transfer rate of graphene is 5,800, whereas water is 0.5. So when these materials are suspended, mixed, substantially thermal performance behavior will be improved. But one of the major challenge is nanomaterials. When we suspend in water in liquid, it may sediment. So that is one of the major challenge called the stability. Okay, and that also related with the pumping power, friction factor when it flows through pipe. So that is major challenge need to be improved. So even though it has good characteristics, but it also has challenges, and that's why we need to conduct research. Next slide, please. So as you can see the behavior of nanomaterials and bulk materials, so surface area is related to this heat transfer behavior. So bulk materials, as you can see, surface area is very, very less, whereas nanomaterials has huge surface area. So if we compare with the nanomaterials, you see it has huge surface area. So this surface area is also very important for thermal and heat transfer areas. For example, when we put our rice in a plate, if it is small, it will take long time to be cooled down. If we put in a big plate, it will be cooled down very, very fast. So that's basically an example of surface area. Nanomaterials, nanoparticle has better surface area, large surface area compared to bulk materials, and that is related with heat transfer. Okay, next slide, please. So these are some of the findings. As you can see, we suspended magazine in palm olein, silicone oil, which has, you have seen, very low thermal conductivity, and as a result, thermal performance, thermal conductivity improved by 68%, and another example, as you can see, it improved by 40%. So these are some of our own results and published in high impact good quality journal. So as you can see, heat transfer performance improved substantially. Next slide, please. So these materials also can be used in clean water production. As you know, the seawater is abundant. Use seawater there, 97% of water is seawater. So this seawater also can be cleaned using these magazine materials. And one of my PhD students is working, and we successfully managed to get the pure water with very high evaporation rate. And we have filed also one patent. We are submitting one copyright, and around 10 papers we are submitting in top-notch journal in the area of clean water purification. And also few papers we published with the KPRIET, that is the Indian Institute. We have collaboration. We supplied the magazine and they applied in desalination, and we managed to publish in desalination journal, which is ranked 3 in the area of water resources. So very highly prestigious journal where we published our work. Next slide, please. So this is our setup by which we clean the water. We desalinate the water, we purify the water, and that purified water also can be used to produce hydrogen. That's actually our future projects. We are working, some of my staffs also working to convert this pure water into hydrogen and so on. Next slide, please. So these are some of the areas. As you can see, we use this magazine in desalination purposes. As you can see, thermal conductivity improved by 40%. This is actually the collaborative work with the KPR IET. And this paper actually, this work we published in desalination, as I mentioned. So this is why our thermal conductivity improvement is important. Next slide, please. We also use these materials in thermal energy storage, phase change materials or battery thermal performances. So as you can see, according to literature findings, so some of the pristine materials called the paraffin wax, these are phase change materials, where as you can see, their thermal conductivity again very, very poor, 0.15, 0.2. When these magazines are suspended, as you can see, their thermal conductivity improves substantially, around 4.2 times higher than the base materials, pristine materials. So in thermal and energy storage, as you can see, the thermal conductivity, thermal performance of pristine materials are extremely poor. As a result, heat transfer, thermal performance, and so on will be very, very poor. So in that case, we use these highly conductive materials, magazine, graphene, CNTs. Their thermal behavior extensively improve. As you can see, these are some of the results we shared here. In some cases, it is 7.2 times higher than the base materials. So this shows that this material is potential. Of course, there are challenges as well. Next slide, please. So heat transfer mechanism, this one I will not go through much. Okay, yeah, next slide, please. So you may want to know the mechanism. So these are some of the slides we tell you the mechanism. Next slide, please. So these, as you know, the materials are clustered. As a result, heat transfer rates are much more faster. Thermal conductivities are higher. So this one, those who are interested to know more about what is the mechanism, what is the theory behind this improvement, can be explained by this called the clustering effect. Okay, next slide, please. These are also called the Brownian motion. With the temperature increase, there are basically called some movement of particles. And as a result, thermal conductivities, thermal performance, heat transfer coefficients are improved. These are basically mechanism, very high level definition or question. Those who are purely working in this area of heat transfer, thermal, molecular dynamic simulation, it is for them. Okay, next slide, please. So these are also the ways using SEM image, TEM image, PSEM, we can explain the mechanism behind this thermal conductivity improvement, energy storage behavior improvement. So structure actually can define why the thermal conductivities or energy storage behavior improve. Okay, so we can use some of the images using TM, PSEM, XPS, and so on. Particularly, I think these are some of the images, I think, using TM. We can see the structure and we can define, we can explain the mechanism behind the improvement. Next slide, please. So the rigidity, as you know, when we use in different application, for example, in fuel cells, so materials or structure may be subjected to twisting, bending. So in that case, mechanical rigidities are important. So compared to graphene, as you can see, it has huge outstanding bending rigidity. So that's why this material is unique in certain aspect, as you can see. Its layer structure, its thermal behavior, its rigidity, and its also optical behavior is also outstanding. It can absorb 100% sunlight. So these are some of the outstanding behavior, unique behavior. One of them is rigidity, as you can see, compared to graphene, it is much more higher. Next slide, please. So these are the layer structure in between layer where molecules, pollutants in waste removal actually can be used. So pollutants, waste actually can be trapped in between layer. That's basically the layer structure and also the surface in pollution removal, and also the ion absorption. For example, we are trying to remove some of the ions of seawater. This is the way basically can be trapped some of the impurities in the desalination water and also in waste removal. Next slide, please. So those are basically in the thermal area. And now let me explain why this material is important in in energy storage, because this is one of the global grand challenge areas, because solar energies are intermittent and we need the energy storage. So we need also energy storage material. So how this magazine can play a great role in storing the energy. That is basically the main purpose it was invented, because its electrical conductivity is extremely high. Next slide, please. So as you can see, these are some of the challenges with the battery, supercapacitor, where power density, specific capacities are very, very poor. So with these materials, some of these challenges can be improved. Some of the chemical reaction also in fuel cell application, chemical reactions are very slow. So with these materials, actually chemical reaction also can be made faster. Next slide, please. So these are actually our Malaysian grand challenge areas. Ministry identified some of the potential areas: battery, fuel cell, supercapacitor, hydrogen. So in the second slide, I showed you where we need to focus. So similarly, in Malaysia also there are some of the focus area need to work. I think similarly, I think the Indian region also, I think there are specific focus, specific areas where need to focus. Research should be with some global grand challenge research areas. So these are the areas where we need to focus. This is just for information, for strategic purpose. Okay, next slide, please. Next slide, please. So these are actually the areas, as you can see: battery, supercapacitor, fuel cell, where as you can see, energy densities, energy behaviors are poor, electrical conductivities are poor, reactions are sluggish. So in our case, we use these magazine materials in fuel cell applications. As you know, the platinums are one of the catalysts, but it is very expensive. So to reduce cost and to replace this platinum with certain amount of magazine, we applied and we got one of the important behavior that is called current density. We got 2.34 times better than the other material. So this is also one of our findings. Some of my staffs also working with the fuel cell using this magazine by making some composite, actually by reducing platinum and some other expensive catalytic materials. And as a result, as you can see, one of the parameters is called current density. It was 2.34 times better than the other materials. Next slide, please. Next slide. So I'm talking about the electrical energy storage, particularly battery, supercapacitor. So one of the important behavior is electrical conductivity. So as you can see, electrical conductivity of these materials are particularly one of the film, as you can see, 24,000 Siemens per centimeter. So that's why these materials plays a great role, and this material is unique in these areas of battery, supercapacitor, electrochemical energy storage. Okay, next slide, please. So this also can be used in, as you can see, in the energy storage for hydrogen energy storage due to absorption and adsorption behavior. Okay, so some literatures are there, and also as I mentioned, we are cleaning the seawater, and then that seawater basically we are converting into hydrogen and oxygen. That is called HER and OER. So this is also in progress. Our preliminary results shows that we got some good result, good finding. Okay, in future we will share with the scientific community. Next slide, please. So we also published in some good quality journals. So these are some of the examples of our publication. As I highlighted, we are pioneer in Malaysia. We are number 1 in Malaysia. So we have published synthesis, application in different areas, in the thermal areas, which is our expertise area. And also recently we started in desalination, clean water and hydrogen production. Okay. So we also published in good quality journals, which you can explore by searching my profile. Next slide, please. So basically those are the technical content. Now I'll be talking about some of our resources, because its purpose is also how we can collaborate. I'm sure that you may have challenges in conducting research due to resources, particularly lab equipment. and also the area of expertise. So I'll be sharing some of these things so that we can collaborate. Your staff, your researcher can work with us. So these are actually the potential areas, emerging areas, advanced materials, emerging materials which I have presented. Energy storage, this is also global grand challenge research areas. Heat, thermal, solar energy. So these are basically our area. Clean water, desalination also recently we have added. These are our potential focus area. We are working. Next slide, please. So we also have PhD program just announced. So you can find in LinkedIn and also in Facebook. I have shared it. So this is very comprehensive scholarship. We have already a number of PhD students from India, from different organizations, fully funded, 3,000 ringgit per month. So this is the highest amount in Malaysia compared to public universities. Normally public universities is 2,000, 1,800. And also it is for 3 years. Okay, so you can find it in LinkedIn. You can contact me also, those who are qualified. CGPA must be 3.5 and need one Scopus Index journal publication to be eligible for this scholarship. So details are provided in my LinkedIn and Facebook profile. Next slide, please. So now I will explore about our research facilities, which is very impressive, as you can see. Next slide. So we built a lab by spending 1.5 million US dollar. As you can see, these are some of the high-end equipment to synthesize equipment for heat transfer, energy storage, thermal areas. So these are actually the very high-end equipment, and our collaborators from India, Pakistan, Bangladesh, Saudi Arab coming and using our facilities. And also locally other universities, students are coming and using our facilities. So we have a lot of collaboration also due to our these outstanding, impressive facilities. Visitors from Harvard, Cambridge, and other top universities came and visited, and they also feel very impressed with our facilities. So this is one of our uniqueness also, and I'm happy to share with you. So if your teams are interested to work with us, there can be a short visit, there can be a joint publication, there can be joint PhD work also, short visit also. So different way basically we can work. So you have seen our expertise, our uniqueness, and also our lab facilities and so on. Our profile also probably you have seen. I think Dr. Rinko also highlighted our achievement and so on. Next slide, please. So these are basically the facilities. I will not talk much. Next slide, please. So you can explore also in my YouTube channel. I have. Okay, next slide, please. Next slide. So this is another area. We have very high-end equipment. We have SEM, we have UBVs, we have DSC, TCA. So these are very high-end equipment for thermal characterization purposes. Okay, next slide. So this is also our strength, even the private university, but very, very strong in number one in ASEAN region, private among the private universities. That's the reason also I joined this university. They gave these impressive lab facilities. I have strong team members and many other good things, unique things at Sanoe University. And they are very rich private company, Sanoe Group. Okay, next slide, please. So to help the young researcher, early career researcher, I also have developed my YouTube channel in addition to my LinkedIn profile and Facebook profile. And for your information, it's actually India is one of the best followers. Normally IITs, IISCs, top Indian institute actually my follower according to my analysis. And this year actually I am